S. Success. Okay, solve it.
Chuck.
Hi and Assalamualaikum. My name is Muhammad Faiz Shauki bin Azhar. Our group will be presenting the applications of second order ordinary differential equations. For our presentation, we will be focusing on mechanical vibrations, which is undamped free vibrations. Our group consists of 6 members. The members is Muhammad Hafiz, Alif Ashraf, Salma Nurdina, Valerie, Nur Ain Yasmin and me. Without wasting any time, let's continue with our questions.
Hello, my name is Yasmin. So first thing first, before we move to the solving problems, we must know what is undamped free vibration means. So undamped free vibration means no damping term, which is B stands for damping coefficient, and no external force, which is Ft equal to 0. Also, the system will oscillate forever. The auxiliary equation or the characteristic equation for undamped system is my squared plus ky equal to 0, which is m is mass in kilogram and k is spring constant in kilogram per second square. As I said just now, the equation is equal to 0 because no external force. As our previous lesson, when the Ft is equal to 0, we use a homogeneous equation solution. So the first step is to find the roots. By using a quadratic formula, we'll get m equal to plus minus bi. The roots consist of the complex number, so the general solution is ys equal to c1 sin beta s plus c2 cos beta s. And then, based on the general solution, we can form the new equation, which is phase form, to find the amplitude by using identity trigonometry formula. And then, we come out with ys equal to a cos beta x minus v, whereas a equals to amplitude and v equals to phase constant. For the amplitude, we use Pythagoras theorem formula, a equal to sert c1 square plus c2 square, and the value of c1 and c2 comes from general solution. For the phase constant v, we use tan inverse c2 over c1. From the characteristic equation, we also can find the angular frequency, which is omega. We use sert k over m or 2 pi f, and the unit for the omega is radian per second. Next, frequency. For the frequency, we use 1 over 2 pi sert k over m, or we also can use 1 over t, which is t means period, and the unit for frequency is hertz. And the last one is period, which is reciprocal to the frequency. Also, we can use 2 pi over 2 pi sert m over k, and the unit is in second. Next, we will move to the another slide to show how to solve the problems of the undamped free vibrations.
Thank you, Yasmin, for the explanation of the introduction. Now we will proceed to the first question in undamped free vibration without initial boundary. The question is, find an equation of motion of the following system and find the period of the system which mass m equal to 10 kg and spring constant k equal to 200 newtons meter. Now we will proceed to the solution. First of all, we need to draw the free body diagram to detect the force that involved in the motion. From the question, we get 2 spring, which means we have a 2k spring constant. So we draw the free body diagram, means fk we have 2 lines. So next, we will take out what the information give from the equation, which is we have mass equal to 10 and k equal to 200 newtons meter. By using auxiliary equation, we have 10y second derivative plus 2 multiply 200 from the spring constant k equal to 0. Now we can find the roots, which is m1 and m2 is equal to plus minus 2 set tan I, which is alpha equal to 0 and beta equals to 2 set tan. So we know that the roots are complex numbers, so the general solution that we get is equal to a cos 2 set tan x plus b sin 2 set tan x. Now we will find the period of the system. The equation period that we know from the secondary school is t equal to 1f, and that also same as 2 pi set m over 2k. We use the 2k because we have two spring, so basically we just use the information of the equation, which mean m equal to tens and k equals to 200 Newton meter. So we get the answer for the period is 0.9935 seconds.
Hi everyone, I am Valerie, and here is our next question, which is about an undamped system with initial value. Okay, the equation, which is a vibrating string with a damping, can be modeled by the differential equation my squared plus with ky equal to 0. The first equation, if m, which is the mass, is equal to 10 kg, the spring constant k is equal to 250 kg per second square, the initial displacement y0 is equal to 0.3 meter, and lastly, the initial velocity differential of y0 is equal to negative 0.1 meter per second. Find the equation of motion for this system. So first of all, we have to insert the value of mass and the spring constant that are given in the equation to generate the auxiliary equation AE. Thus, we can find the value of the roots m1 and m2, which are imaginary number plus minus 5. After that, we can find the value of alpha, real number, and beta, imaginary number, which are 0 and 5 respectively, from the value of the roots. Next, we can generate a general equation from value of alpha and beta, which is yx equal to a cos 5x plus with b sin 5x. Then, we have to differentiate the yx equation, thus it will become differentiate of yx equal to negative 5a sin 5x plus with 5b cos 5x. From the initial value, y0 equal to 0.3 and differentiate of y0 equal to negative 0.1, we have to insert the value of x and y respectively on both yx and differentiate of yx. Lastly, we can find the a and b value from this insertion. So, the final value of a and b that we get are 0.3 and negative 0.02 respectively. So, the equation of motion for this system, which is the final answer, will be yx equal to 0.3 a sin 5x minus with 0.02 sin 5x. The second question will be explained by Salma. Thank you.
Next, I will continue to explain for the second question, which is when the equation of motion is of the form displayed in question 1, the motion is said to be oscillatory with frequency beta over 2 pi. Find the frequency of the oscillation for the spring system of part 1. So, from the question given, the system is said to move with frequency beta over 2 pi. So, from here, we can use this formula to find the frequency of the oscillation for the spring system. After that, we just need to insert the value of spring constant, which is 250 kg per second squared, and mass 10 kg that we obtained from the question given into the formula. Lastly, the final answer for the frequency of the oscillation for the spring system will be 0.8 Hz.
That's all from us. Thank you and see you in the next video.
Principal, this is how far the board can carry. So this is the answer for now.
Wow. This is good.
Principal, you see this is wrong. She's absolutely wrong. She's practically repeating the same thing in different sizes.
Ha! You mean to say this is not the correct answer?
Yes, it's very wrong.
Auntie, is it not How you that say I should expand this equation?
Success. When I said expand, I don't mean literal expansion. I mean mathematically expand this equation.
Teacher that doesn't know how to speak English is that one teacher. Okay, then why didn't you write mathematically expand this equation? See, auntie, if you want to speak English, speak it well. If you don't know how to speak it, you leave it. Uncle, let's go, Joe. Be talking with your nose like bird that's looking for food. I teach you primary 2 people S and Y.
Don't mind her.
Principal, you see what I'm trying?
Hey! So this is how you be harassing students in this school?
No.
A child will solve something correctly, yet you flog the person.
Principal.
Hey! You better pack your things and leave this school. You are fired!
Principal, help.